Last time we introduced the D-square law. I want to mention again, based on the fundamental consideration, actually the D-square law was formulated based on the two regions. One region focused on the gas phase region bounded by the liquid phase and very far away environment. And in this region, because I think about the variation of gas property is more fast compared with the regression of your liquid surface, because in the evaporation or combustion process, droplet continues evaporate the liquid fuel as the vapor out. That means the liquid surface should be continuously decreased. In this degradation process, then you will find out the problem should be the unsteady problem. But in reality, if you focus on the gas phase phenomena, those gas phase property change very fast. Is even 1,000 times of the variation of your liquid surface. In this sense, we can say for the gas property change in in gas regions, we assume they are quasi-steady. Quasi-steady means not exactly steady, but very similar, and you can assume it is a steady. Then we use the steady state assumptions and to analyze the gas phase property change based on the mass conservation and energy conservation. And we will have the expression for mass flow rate in this region, gas phase. And this mass flow rate actually should be balanced with the vapor coming out from the liquid surface. That means that you need to study the mass coming out from the liquid phase based on the unsteady problem for droplet evaporation. Now you stand just on the liquid surface, then liquid droplet, and to think about the liquid surface continuous change as in the regression period. And by connection, these two mass flow rate, because the evaporation the evaporation of liquid vapor coming out from a liquid surface is equal to the flow flowing in the gas phase. They should be balanced and they should be the same. And we meet at the liquid surface boundary, then you can have a solution. And here, that means I emphasize for the gas phase, we assume this is a quasi-steady considerations, and for the droplet itself is unsteady problem. And we think about the whole geometry are perfect because the droplet is a spherical and stagnant, and in the whole environment is also stagnant. We neglect those kinds of influence coming the buoyancy, but buoyancy effect basically is very important, and also flow conversion, and we will discuss it later. Based on these kinds of consideration, then we can have some formula be used for the for the estimation on the combustion characteristic of droplet combustion. Here, the first one we say the flame location. Flame location actually this we call this RF tilde is equal to RF divided by RS. As you understand in the real situation or in the experimental observations, you will find out the flame positions RF, the flame position for the droplet flame, and the droplet radius, actually they change with respect to the time. Okay, which means when you use this do the comparison RF to the basically they represent the so-called the stand-up ratio between the liquid surface and also the flame the flame surface. Okay, that means in this region the size of this region between the liquid surface and the diffusion flame can be estimated by RF tilde, and RF tilde can be found is governed by the two natural log functions and represented in the denominator and the numerator both. And then the most important thing, I try to introduce the definition on the so-called the Spalding number S. And the upper formula represent used for the combustion, the lower one used for evaporation. But you can see for both formula for combustion and evaporation, in the denominator, they only use the L. L represent the latent heat or evaporation. Here, you should remember I use assumption for the D square law. For the D square law, we do not assume the preheating of the droplet. As you remember, I emphasized when you have a droplet, have a liquid jump into a hot environment, since initially the temperature of your droplet is low, you need to have some heat transfer into your droplet to heat it up to let the temperature, especially for the droplet surface temperature, reach to the Weber temperature, very close to the boiling point, but not the boiling point. The temperature required for evaporation or start to have an evaporation basically defined as a boiling point. As we mentioned, we treat the liquid as a pure substance, and the vapor coming out in a pure substance environment. But in reality, we have a pure substance. For example, you have a high purity of the fuel, but actually those fuel will exist in an environment that contains certain amount of nitrogen and oxygen. That means the composition of air. When you have some vapor coming out, then you will meet the oxygen and the fuel and the nitrogen together, which means you are in the mixture conditions. You cannot treat it as a pure substance, which means you are considering the pressure in the partial of the pressure in the environment should be described by so-called partial pressure, because you need to think about the nitrogen, oxygen in the environment. The vapor coming out near the surface, basically they are dominant, but there's certain amount of oxygen and nitrogen mixed together. Then when you think about the partial pressure, then it's smaller than the pressure for the pure substance evaporation. Then the temperature for evaporation is smaller than the regular boiling point for the pure substance. Okay, I need to emphasize this. And that means that when you think about the real liquids gasified, either evaporation or burning, they always go through the evaporation process. But you should remember the environment is a mixtures. Okay, then the temperature required for evaporation is smaller than the boiling point itself defined based on pure substance, and this corresponding to the so-called Weber temperature. Okay. And here you can see the L. L represents, we just think about the latent heat of evaporation without consider the preheating. If you consider the preheating, then you a small amount of heat for preheating will be add to the value in the denominator, okay, plus L, the latent heat of vaporization, okay. And L represents the heat required be absorbed by the droplet to go for evaporation. And the denominator represents how much heat transformed from the surrounding to your droplet. For evaporation, for vaporizations is simple, because those can be calculated by enthalpy difference between the far environment and also the liquid surface, right? It's a H infinity minus HS. And if you consider the ideal gas, then they can be presented by CPG T infinity minus TS. TS represent the droplet surface temperature. Okay, this is for vaporization, but for combustion, since you have additional burning flame surrounds your droplet, that means that the heat of the combustion released through the diffusion burning will have another contribution to get the heat and the transport to your droplets, which means in the denominator of the upper formula tell you there is some heat coming from the temperature difference between the surrounding and the droplet surface, this is a certain amount of heat, and usually this is a small amount. And the second term represents the heat release by the diffusion burning. And Q, you understand this is a heat of combustion per unit mass of fuel, right? But I will use this YO infinity divided by sigma. Actually, this is corresponding to how much oxygen should be used to burn out 1 kilomole of fuel. Sigma represents the stoichiometric ratio, as we mentioned in the very earlier starting from the class. Okay, then this is the heat provided by diffusion burning at the heat transfer from the outer surrounding to the droplet. Then these two heat will be used to help the droplets absorb and overcome the latent heat evaporations. Then from those kinds of definition, you will figure out the driving force. Here, the Spalding number, actually this is initiated by the Spalding, then we call this as a Spalding number, very famous scientist, and they give this very famous transport number used for very simple description on droplet evaporation under low temperature environment or under diffusion burning. Now, they say if you look at the denominator, actually we can see this basically is a resistance. What is the meaning of resistance? Resistance means if you have a large latent heat of vaporization, you need more heat to transfer to be absorbed, right? It's some kinds of resistance. But the driving force basically coming from the denominator, okay? The heat transfer from the surrounding and also heat transfer from the burning has a big driving force to provide energy to the droplet, and the droplet will absorb it to gasify vapor out of the liquid. Okay, and mass flow rate of a given droplet, you can see, can be found described by this formula. M is mass flow rate of the fuel vapor coming out from the liquid surface is equal to 4 pi rho g dgRs. Okay, here you can see the diffusion coefficient in the gas phase is a very important role. It's a linear dependence for the mass flow rate. And then here again, you have a natural log 1 plus S. If you have a large Spalding number, then your mass flow rate will be stronger. Okay. And the next equation is very interesting and very important. They give you the energy balance for a given flame. Okay, now you have a diffusion flame, right? Then diffusion flame has the fuel coming in from the droplets and oxygen coming in from the surrounding. They meet together and burn. And you assume at the flame, the diffusion flame, you will burn 1 kilomole, 1 kilogram of fuel. Then they will release Q, right? Q represents the heat of combustion per unit of per 1 kilogram of fuel. Okay, and this heat will be supplied because we know the diffusion flame. When you have when you release the heat of combustion, those heat will diffuse to the fuel side and also to the oxidizer side, right? Okay, now you can see here they diffuse the part of the heat diffused to the fuel side. Those heat can be used for L. Okay, here you can see that this bracket. Then in front of bracket you can imagine there is the one here. Okay, 1 kilogram of fuel. Okay, now those heat will be used for 1 kilogram of fuel have a latent heat of evaporation L, and when they evaporate, become a gas vapor, they will be heat from the surface temperature, because very in the vicinity of liquid surface, the gas temperature is very, very close to the surface temperature, right? It's about temperature. And this temperature will be increased to the flame temperature, okay? Which means in the fuel side, okay, those vapor, they come in from the liquid surface, and why they can come out from liquid surface, because they already absorb the latent heat of evaporation, and then they diffuse to diffusion flame, In this region, when they diffuse, they absorb the heat that the temperature starting from the Ts increase to the Tf. Okay. The bracket represents the heat will be absorbed by fuel in the fuel sites. Okay. The other part, those heat will diffuse to the oxidizer sites. In the oxidizer site, how much oxygen can be diffused into the diffusion flame basically can be defined by YO infinity divided by sigma, right? This value is corresponding to 1 kilograms of fuel burned out. And you will find out this amount of oxygens, okay, 1 divided by YO infinity divided by sigma, you reverse it and then represent how much oxygen will be used for the burning, for the diffusion burning, or in a sense, how much oxygen can be heat from the surrounding temperature T infinity increase to the Tf. Okay, the first term represents how much heat will be diffused to the oxygen regions, okay, oxygen environment. Now you can clearly understand from this formula that tell you the total energy needed to heat the oxidizer from the T infinity to Tf, as well as to gasify the fuel and then heat it from Ts to Tf is the total chemical heat release Q. This is basically tell you the energy balance for this droplet burning based on the D square law. Now, as I mentioned, there's an important matching at the liquid surface when you have a solutions from the gas phase. Actually, the first formula for flame locations and the mass flow rate and also flame temperature were justified from the theoretical formulation based on the gas phase environment. And you can follow the unsteady problem to study the droplet evaporation under the heating. Then you can have connection between these two mass flow rates together at the liquid surface. And finally, you will find out there is the so-called D square law. This is a basic, a very familiar, very famous formula to describe the ds represent the droplet size at any instance, and the square equal to the initial droplet size minus kt. That means that d square, this s square means that we are talking about the surface, right? D square means surface. That means the droplet surface actually is linearly decreased with respect to the time. And there is the constant, so-called K. This is a evaporation constant, and K is equal to A times rho G dG. Rho G means the density of your gas phase, and dG is the density in the gas phase, and rho L represent the liquid density. Here we still have this function natural log 1 plus S. Okay. This K basically is totally controlled by the environment. Okay, if the S represents how much heat you transfer, right? Okay, depends on the heat released from the burning and also the environment temperature. Okay, and you can see there is the K. Usually K, if K is large, that means the droplet lifetime will be short. Okay, and then if you plot as the D square burst times, you will see there is the linear lines, and the K will be the slope of the line. I will show you later. Here they tell you, here this is the evaporation rate. Usually for the D square law, K is a constant, and simply you just have a linear lines for the D square verse T curve. But here they mention, later on I will show you from the experimental observation. For a real observation in the experiment, the initial evaporation rate is low because the droplet is cold. Then you will need to have some energy to heat the droplet up. Okay, at that instant, at that period, short period, the droplet size almost do not change. However, when the droplet temperatures closer to the vapor temperature, then droplet heating will be over in an earlier part of the droplet lifetime. Therefore, the subsequent regulation rate of droplet surface area or equivalently is the diameter square will remain constant with time. I will explain it based on the experimental observation. Then we go to the experiment system that you know. People usually use this very famous so-called free-falling droplet experiment and to study the droplet. Okay. Yeah, basically, this is a system. Okay, let me explain first about the whole system. There is the droplet generation unit. Okay, and they will generate a string of the droplets coming from the upper side to the down to the lower side. And here there is the flood flame burner. Okay, we generate the flood flame, then droplet penetrates through the droplet flame will be ignited. Okay, and the special techniques will be used for this kinds of experimental observation. We will have a strobe light accompanied with the camera. They will control by the same frequencies. Then you can frozen. The droplet will be frozen, and you can see the single droplet stay in different positions, and you can take pictures and measure the droplet size and to try to confirm the variation of your droplet size based on the D-square law. Okay. Here, this is enlarged pictures to let you know. Here you can see we can purge air. We can have an air supply, and also there is a flood flame burner to generate flame here, and the fuel will come in from the since we have a flood flame here, you need to have some gaseous fuel coming in with air. Then they mix together to generate the premix flame here. The droplet will be generated through this tube into the chamber. And here, this is the droplet generator. We have a nozzle here. Okay, this can be used quartz glass, or actually normal glass is okay, but usually you need to prevent heating. Usually the injector is slightly away from the flood flame. They exist in a cold environment. It is not necessary to use the quartz tube, but you can use the regular or normal glass tube. And the liquid coming in, and then we use the transducers, electric transducer to produce the pulse motion, and those pulse motion were acting on the liquid inside of the injectors. Then they will give you the periodical motion, then push your droplet coming out. Later on, I will explain those kinds of breakup mechanism based on those kinds of disturbance. But anyway, when you give the control frequency to produce a pulse, the pressure variation on the liquids, then you can generate a string of the droplet surface. Here, this is a typical image to tell the single drop. You can see the break point, ports that represent the droplet coming in from A to A, B, C, D, E, F. Actually, we try to change the frequency. A has a higher frequency, then you can see the droplet separation distance is smaller, but when you decrease your frequency, the separation distance will be changed. And by those kinds of frequency variations, you can study the different kinds of you can discuss the influence coming of droplet separation, because this droplet separation distance is a key factor for the spray combustion. Then if you have a larger separation distance, that means the droplet and the droplet they have a separate with a longer distance, and you can have more air to mix with a fuel vapor easily. Then usually we look at those kinds of spray as a dilute spray. Okay, but when you have droplets, they have a closer separation distance. Then you have so many droplets in a given control volume. Then the spray, we call this as a so-called a dense spray. And the air cannot penetrate efficiently to mix with the fuel vapor. Now I just mentioned this is a good experiment techniques to be used to study many subjects on the droplet combustion application. Now I want to show you the experimental results, but I need to change it to the slides to let you know more detailedly. So I stop here, and then we will use the PowerPoint to let you know clearly from the experimental observation.